Up until now, you've worked with the extrema on an interval, which were critical numbers would find extrema on an interval. We've looked at extremely high y values where they'll appear at the top of a hill. We call that a relative extrema. And we've also explored the notion of absolute extrema, in which you need to look at both the endpoints and the relative extrema to determine the absolute highest y value. So make sure that you make a table and you look at both when you're doing that. Today what I want to look at in this video, I want to look at what's called Rolle's theorem. And Rolle's theorem and the mean value theorem are really nothing more than a promise. Now, when you get a theorem that is a promise like this, what you want to do is you want to first make sure that your problem satisfies all the requirements. That's first. And then second, if it satisfies the requirements, then the promise will be fulfilled that is in this particular theorem. Let me explain to you what Rolle's theorem says. The definition of Rolle's theorem is the following. First, it's got requirements. And here they are. The first requirement of Rolle's theorem is that f of x is continuous. On a closed interval. And that's from a to b. And that's x equals a to x equals b. So, right away you know that you don't have to worry about discontinuities of any kind. You don't need to worry about vertical asymptotes. You don't need to worry about those little tiny undefined spots or anything like that. This is a nice continuous curve from A to B. Now, it doesn't say anything about sharp corners, yet anyway. So, if I were to draw this curve, I'd put my pen on the page at A, x equals A, wherever the y value is, and then draw it to x equals B, and it would be continuous. Electricity would flow through that circuit pretty well. Here comes the second requirement. The second requirement is that f of x is differentiable on the open interval. And that's from A to B, but not including A and B. Now I want you to think about why they make it or ask for it to be differentiable on the open interval but continuous on the closed interval. To be continuous on the closed interval simply means that the endpoints are there, they're solid, you can access them, they're dots. The derivative, though, the derivative doesn't exist at endpoints. If you just look at an interval from A to B, the derivative doesn't really exist at x equals A, and it doesn't exist at x equals B either, because don't forget where derivatives came from. They came from a limit process. And in order to answer a limit question, you have to come at it from both sides. Well, you can't do that at an endpoint. So what we say at the endpoints is that it's non-differentiable, meaning the derivative is undefined. We don't say derivatives do not exist, by the way, like we do limits, even though it's born of a limit. Derivatives are generally functions, and functions are generally undefined. So we already know that at any endpoint, no matter what, it's non-differentiable. But we make the requirement that everywhere in between that it is differentiable. So what does a differentiable continuous curve look like? I almost gave it away. They're smooth curves. This implies smoothness. Why does it imply smoothness? Because if it were non-differentiable at a point here between A and B, we already know it's continuous, so I can't leave the pen from the page. So how do you draw a continuous curve where the derivative happens to be undefined at some location? You must have a sharp corner. Sharp corners are non-differentiable. So this implies smoothness. And the last requirement is that the f of A is equal to the f of B. This is on a closed interval, and all it says is that the y values match. What I might do with Rolle's theorem, if I ask you a question about it, is I might say, number one, can you tell me if this particular scenario fulfills the requirements of Rolle's theorem. So in order to do that, you're going to have to answer the question about continuity. You're going to have to answer the question about differentiability, and certainly you'll answer the question about the y values matching. All three of those are things you can do. To determine if y values match, simply plug x equals a and x equals b into the function and make sure that the y values match. That's not a big deal. To make sure the function's continuous, find out where the function might become discontinuous. And where would that happen? Generally, dividing by 0 or square root of a negative number. So if you detect that you're going to take the square root of a negative number or divide by 0, you can say, no, it's discontinuous. If that discontinuity falls outside of your interval, we don't care. Differentiability, how do you deal with that? How do you know it's smooth? Well, get f prime, and f prime is your new function, and say, when is this function undefined? Because when it is, it's considered non-differentiable. So you got f prime out there, you look at it, if it's a fraction, same thing. You look down the denominator and say, what would cause it to have a division by 0? What would cause it to have a square root of a negative number? If those x values also fall within your interval, you would say, no, this does not fulfill Rolle's theorem. So if they fall outside of the interval, we're okay, because we only look at this one window. Okay, so why don't we take a look at the picture. I want to see what it looks like to fulfill these requirements. So I'm going to draw a curve that fulfills all three requirements of Rolle's theorem, and then, finally, I'll give you the promise that Rolle's theorem makes. So here's our function. Here's x equals a right here. Closed interval, here's x equals b. Now it does say that the f of a must be the same as the f of b. And why don't we put that down here? That'll be my y value, and I'll come across here and make that my y value over there. Okay. The y values endpoints of the endpoints match. Now, I got to draw a curve now that's continuous and smooth, meaning I'm not allowed to have any sharp corners. I'm not allowed to have any breaks. Okay, so I'll draw a continuous smooth curve. As long as it's still a function, we're okay here. There we go. So, this function right here fulfills the requirements of Rolle's. On the interval from a to b. We can say that with confidence here because you can see that it's continuous and there do not appear to be any sharp corners. Now, if it were a function where f of x is defined for you algebraically, you can't just say that it fulfills Rolle's theorem. You've got to show me that it's continuous. Show me that you won't divide by 0. You can't say that it's differentiable throughout the interval. You've got to prove that. And the way to do that is take f prime and show me that that never becomes undefined, at least within the interval. All right, now, finally, that we've got the requirements met, what does Rolle's theorem promise? This is what Rolle's theorem promises. The promise. The promise is that there exists at least one x value, perhaps more, where f prime of that magic x value is 0. So what is the promise? I guess the promise is for a continuous, smooth curve where the y values match on the endpoints, they're promising you critical numbers. So the promise is there are critical numbers somewhere within this interval. But not just any kind of critical number, only this kind of critical number. That would be a hill, a valley, or a flat spot. Those are the only kind of critical numbers you will find when f prime is equal to 0. You will not find the other style of critical numbers, and you need to remember what those are. There's another style of critical number, and that's when f prime is undefined. And f prime will become undefined for a variety of reasons, but one reason is because the function itself is undefined. Not going to happen here. We have a continuous function. The second reason that f prime will become undefined is because of a sharp corner. That makes f prime undefined. We're not going to find that because this is a smooth differentiable curve. So the only critical numbers that we are promised are these. You will not find any others. Let's go up here and find those fulfilled by that promise. Are they there? Here's one. Here's another one. And a third. And right here, a fourth, a flat spot. So yes, we did get our promise fulfilled. There are actually four of these critical numbers of this particular flavor anyway, because these are all going to be horizontal tangent lines. There's one there. There's one there. There's one there. And there's one here. Okay, that happened to be a flat spot. So Rolle's was right. So basically, if you do have a continuous curve, if you know that it's smooth, meaning there are no sharp corners, because a sharp corner means that the derivative is not defined at that particular location, so we have to make sure the derivative is fully defined everywhere on the interval, then Rolle says, I promise you that there's a critical number somewhere between A and B, maybe more than one. In this case, we found 4 different critical numbers. Okay. What would happen if we removed one of these criteria? What if we remove the requirement that f prime needs to be defined, completely defined throughout the interval? So here we go. First requirement, f of x is continuous. Second requirement, f of x is differentiable or smooth. Third requirement, f of a is equal to f of b. What if we removed this requirement? What would happen? Here's what the curve would look like. Here's a, here's b. The f of a is still going to be the f of b, whatever y value we choose that to be. It has to be continuous. I can't leave the pen from the page, but I am now allowed to have a derivative that is undefined. Electricity will certainly flow through there, but where is the promise fulfilled? See, so in order for Rolle's to be satisfied, you must have all 3. Here, I put a sharp corner in. Nope, sorry, that's not differentiable at that location. F prime comes out to be undefined at that location, not 0. And look around. There's no other place where we're going to get f prime to be 0. So that is the basis of Rolle's theorem. I think what we ought to do here is maybe do an example. Here's the example. F of x is a parabola. First part of this example will be, let's find the x-intercepts. Remember how to find the x-intercepts? You set y to 0. Now, why did I pick the x-intercepts for this problem? Because here they are. The reason I picked the x-intercepts, and I thought they would be interesting places to go, is because that could be my A, that could be my B, and that will satisfy rule number 3, or criteria number 3, on Rolle's theorem. Rolle's theorem says the f of A must be equal to the f of B. Is that really true here? The f of -1, are you really equal to the f of 6? Well, of course they are, because they're x-intercepts. So therefore, if you put -1 or 6 into your function, you get 0. In fact, we selected y to be 0. So each one of those will cause y to be 0. So number 3 is already satisfied. So basically, the y values of the endpoints will definitely match. And that is a requirement of Rolle's theorem. You can't really do it without the y values matching. Well, we skipped ahead. Let's go to the first requirement. Is f of x continuous? Now, this time you have an algebraic expression. You have a function written down. You need to prove to me that it's continuous. Well, there's really two things that are going to cause it to be discontinuous, and that's the square root of a negative number and dividing by 0. Let's take a look at the function again. No square roots and no division at all. So there's no division and no radicals, really. So we don't have to worry about this thing ever being undefined. So if the domain is all real numbers like it is for this one, then, well, certainly it's continuous. There are no x's that will ever cause this to be undefined. In fact, I will say this, all polynomials are continuous for the entire domain. So it's a polynomial. No division, no radicals. Definitely continuous. Number 2, differentiable. That means f prime, which happens to be 2x minus 5. Now be careful with this word differentiable. Because it's got the word able in it. And some people think that differentiable means I'm able to take the derivative. You will always be able to take the derivative. The question is, does that derivative become undefined within your interval? And the answer is, not for this function. Look at your derivative, another polynomial. There's no division, no square roots. So how could it possibly become undefined? In fact, the domain of the derivative is all real numbers. Well, it's differentiable. In fact, all polynomials are differentiable, which implies that all polynomials are smooth. That's another thing to note. They're all going to be smooth. Smooth continuous curves. So, with that in mind, here's what I'd like to do. Does Rolle's theorem apply for this function on this interval? That would be the first question you will get for a Rolle's theorem problem. Does that apply? And we've already gone through the three-step checklist here. Number 1, continuous. Yes, and you need to tell me why it's continuous. No division by 0, no square roots, nothing to worry about here. Even if there was a division, and maybe that division had an x minus 2 in it on the bottom, it would be undefined for x equals 2. Okay, so then it would not be continuous on the interval. But if it had an x minus 7 in the denominator, we're okay with that because the discontinuity falls outside. So it's continuous, and you need to explain why. Number 2, is it differentiable / smooth? Again, you need to explain to me why it is, and we did just that. The derivative is 2x minus 5, and that will never become undefined. So it is differentiable smooth throughout the entire interval. Now, it could be non-differentiable at x equals 7, and I'm okay with that, just as long as it doesn't fall within my interval. And the last, of course, is the f of a equal to the f of b, and we certainly proved that. These are both x-intercepts. Both y values are the same. They're 0. Yes, Rolle's applies. Okay, what's the promise? Let's fulfill the promise, guys. The promise is somewhere on the interval, and we'll go from -1 to 6. Somewhere on the interval, there is some x value, at least one, where the f prime is equal to 0. So it's calling it out as a critical number, but of this flavor only. That means hill, valley, flat spot, not going to be a sharp corner, which also is a critical number. We need to take that into account. Now, somewhere on this interval, there must be a critical number. That's the promise. Let's see if the promise is fulfilled, guys. We know how to find out where that happens. F prime of x was 2x minus 5. And let's find out when f prime is truly equal to 0. 2x is therefore equal to 5. And we'll call it c, I guess, is 5/2. Truly does lie within the interval. So that is a good example of Rolle's theorem right there. You have to really show that the requirements are met very carefully. And if there is a division in your function, you would say, well, when would I divide by 0? And if you divide by 0 for x equals 7, that's outside the interval. We don't care. If you divide by 0 at x equals 3, we do care. And we say, no, Rolle's doesn't apply, and you can just stop right there. Notice that I gave you the promise. Promise was f prime equals 0 somewhere. In other words, that flavor of critical number is in there somewhere. And then I went to the derivative and proved that it actually worked. So Rolle's theorem is actually a good way to narrow down, without calculus, where you should run into critical numbers. No calculus is needed to get that interval and do step 1, 2, and well, I guess to do differentiability, you do need some calculus. So that's not necessarily true. So let's proceed and look at one more example of Rolle's here. So let's make this a little quicker, and we're going to see if Rolle's applies to this problem. I'm going to use example 2 in the book. So f of x is x to the 4th minus 2x squared. And the question is, does Rolle's apply, first of all? Does Rolle's apply? Well, number 1, continuous. Yes, that's certainly continuous. There's no division by 0. There's no square roots. And by the way, it's a polynomial. So, yes, certainly that applies. Number 2, is it differentiable? Which differentiability implies smoothness. Is it smooth? Well, differentiability is not your ability to take the derivative. I think you should be able to take the derivative here. This is 4x cubed, and this becomes 4x. Question is, does this ever become undefined? Well, there's no division by 0 possible, and there's no square root. In fact, this came from a polynomial, so polynomials are always differentiable. So that one pretty quickly. And finally, number 3. Let's see if they got this right. Does Rolle's apply? Oh, didn't give you the interval. So let's pick an interval here. The interval I'm going to choose will be -2 to +2. Let's try it. Is it true, guys, that the f of -2 is the same as the f of +2? The f of -2 would be -2 to the 4th power minus 2 -2 squared. Does that really equal to 2 to the 4th power minus 2 times 2 squared? This is 16, and this is 8. This is 16, and this is 8. It's a big check. So what does that mean? Promise. Rolle's theorem promises you that somewhere on this interval there must be at least one critical number of the variety f prime equals 0. At least once, maybe more. Okay, now it's time to fulfill the promise. Let's do it. F prime, which is 4x cubed minus 4x. When are you equal to 0? Now I got to tell you that when you do this, it is possible that you will find some x values that are outside the interval. I don't really care about those. You can have as many as you want outside the interval. Rolle says, hey, on my interval, I promise you at least one. So at least one better fall within this interval from -2 to 2. Let's do this. 4x. X squared minus 1 equals 0. Factor out the 4x. Divide by 4. Nobody cares about the 4 in terms of solving this problem. Let's get rid of it. Oh, we can factor this, can't we? That's going to be x plus 1, x minus 1. So what are our critical numbers, at least of this particular flavor of critical number? There's 3 of them. So who knows how many that you would get? But we got 3 of them that basically said that Rolle's theorem was satisfied. So what does this thing look like? Well, if you were to look at this particular function, it kind of looks something like that. So if you look carefully at it, what you see is that between -2 and +2, you definitely have the y values matching at the endpoints. It is a smooth differentiable curve. And there they are, 3 critical numbers of this particular flavor, f prime equals 0, and they're all located within the interval. That's all Rolle says. Rolle says requirements and promise. Now, if one of those fell outside the interval, remember I said we don't really care about that. But if they all fell outside the interval, something's wrong with that. Okay, Rolle says no, at least one needs to fall inside this interval. Now I'm going to show you the next theorem called the mean value theorem. We'll finish with that. Now what the mean value theorem says is the following. Just like the Rolle's theorem, we have requirements. First requirement, number 1, continuous. We've seen that one before. Number 2, second requirement, differentiability, which implies smoothness. Third requirement, we don't have one. Therefore, it's easier than Rolle's in that regard. So there's only 2 things to look for. Function's continuous, just make sure you don't divide by 0 or take the square root of a negative number. And the function is differentiable or smooth on the interval. Now the promise. The promise that mean value theorem makes is that somewhere on the interval, and I got to put that up here, these requirements are certainly on the interval from A to B, both of them. Somewhere on this interval, actually that should be like that, because we don't look at the endpoints necessarily here for this promise. Somewhere on the interval, the slope of a tangent line to my curve will be equal to the slope of the secant line. That is the promise. I'll be really careful here because I would say that that occurs at x equals, C1, C2, however many we get. But be extra careful. These are not critical numbers. You'll see in the picture I draw next that they just can't be critical numbers. It's impossible. Now, let's draw something a curve where mean value theorem would apply. We go here to our closed interval from A to B. We make f of A down here, but let's make f of B elsewhere, up here. They don't have to match anymore, and all I got to do is draw a smooth, continuous curve. So let's draw a curve like that, something like that. This is going to be f of A. This is going to be f of B, And the very first thing you should do is determine the slope of the secant line that connects the endpoints. So I'm going to connect the endpoints and draw the secant line. Here it is. By the way, if this were a position versus time curve, the secant slope has a very special meaning. It represents the average speed. Now, it is continuous and smooth. The endpoints don't have to match. And what does the mean value theorem promise? It promises that somewhere you will get a tangent line whose slope matches the secant line. Let's find it. Parallel. Right there. So let me draw this tangent line that happens to be parallel to the secant line. Where does this happen? Well, on this curve, it only happens once, right there, whatever that x equals c value happens to be. And that is the promise. Well, what is the slope of the secant line again? We don't need calculus for that. It's rise over run, and the rise is a change in the y value and over a change in the x value. See, no calculus is needed for that. But to get the slope of that tangent line, you would want the f prime at x equals c to just happen to match the slope of the secant line. And that's what we're going to have to do here. So let's take a look at an example. Okay. Let's try problem 37 from the homework. It says the f of x is x squared, and the interval is from -2 to +1. All right. Number 1, continuous. Yes, because it's a polynomial. There's no division by 0 even possible, and there's no square roots either, so there's no way to make this function undefined. Number 2, differentiable. And that would be also yes, because it's a polynomial. All polynomials are continuous and differentiable. There's no dividing by 0, there's no square roots. So yes, it's differentiable. And luckily for us, that's all the mean value theorem asks for. We can stop. So, what's the promise? The promise is that somewhere on the interval, the secant slope matches the tangent slope. That's the promise. And your job is to be able to figure that out. So, I didn't differentiate here. Let's do that here. And actually, this is the function you're supposed to be checking, that square root or divide by 0. So, f prime is 2x. All right, when will the secant slope match the tangent slope? And the promise is this happens on the interval, let's say within the interval, from -2 to 1. That is the promise. Somewhere you better find a tangent slope that is equal to the secant slope on the interval. Not 0. We're not doing slope 0. That would be critical numbers. That would be Rolle's theorem. We better find the secant slope then, huh? And we don't need calculus for that. It's the f of 1 minus the f of -2, and it's 1 minus -2. That's rise, change in y, run, change in x. Well, we see what the function is. It's x squared. So that would be a 1 squared minus a -2 squared all over a 1 plus 2. The secant slope is 1 minus 4 over 1 plus 2, -3 over 3. Secant slope is -1. On this particular interval, the secant slope is -1. Let's fulfill this promise. Again, we want f prime at some magic value c to be equal to the secant slope, -1, not 0. For the mean value theorem, we set the derivative equal to the slope of the secant line, which typically won't be 0. So you remember what f prime was. F prime was 2x. So therefore, 2c, 2x, 2c in this case, when are you equal to negative 1? Not 0. And that happens at negative a half. Which, by the way, fulfills the promise, because negative a half falls within the range of my interval, negative 2 to 1. It falls right inside. There was only one value that we found, so it better fall inside of our interval. What does the picture look like? This is x squared. This is negative 2. This is positive 1. Here comes the slope of the secant line. Slope of the secant line, right here. We calculated that to be a negative 1 slope. Where would you find a slope to be parallel to that? Right there. And what is there? Not strangely enough, really, that is negative a half. That is what we expected. That's where we expected it to be. Now, the interesting thing about the mean value theorem, once I've drawn this, is that this is nothing more than Rolle's theorem on its side. If I take this entire picture and I just keep rotating it, check it out. Rolle's theorem. This now looks like the two y values are at the same level, and this looks like the location of a horizontal tangent line. It looks just like Rolle's theorem on its side. So what I have to say to you about doing these problems is I'm going to ask you for the 3 requirements, and you've got to prove all 3 are worthy of these theorems on Rolle's theorem. And then, of course, on mean value, there's only 2 requirements. And then back it up and say what the promise is. Now, for Rolle's theorem, the promise is f prime equals 0. You will get critical numbers of that particular flavor. And you're supposed to have at least 1 in there. Then go and prove that you really do have at least 1 by doing f prime equals 0 and solving. Mean value theorem, do not set f prime to 0. Set f prime equal to the slope of the secant line. You have to calculate what that is. And then find out what x value causes that to happen. That's what we're looking for. So, again, knowing that the secant slope represents an average speed if this were a motion problem, that's what secant slopes do. And the tangent slope represents an instantaneous speed. So what does that tell you? In practical terms, it says, okay, if you have a continuous, smooth function, like your car driving on the highway, okay, that's a continuous function. Unless we have technology from Star Trek to transport the car from one place to the other, you must continuously drive from A to B. Second, it's a differentiable function in the fact that there are really no sharp corners in terms of your position. It's a continuous function. It's a smooth function when you're driving on the highway, more or less. And so then the conclusion, therefore, based on the mean value theorem, is that somewhere, let's say you take 2 mile markers, mile marker 1 and mile marker 100 or something. Mile marker 0, let's say, and 100. That's a 100-mile stretch. You're driving a continuous, smooth driving vehicle. You calculate your average speed. Let's say it turns out to be 70 miles per hour. One number, no calculus, just calculate average. Distance over time. The mean value theorem now says that because it was continuous, because it was smooth, somewhere along your journey, your instantaneous speed, that means your speedometer, must match your average speed of 70 miles per hour. That's pretty much common sense. How do you get an average speed of 70 miles per hour? Well, your speedometer has to come up to 70, probably 80 for a while, and then back through 70 to 60. So, in fact, on that trip, your speedometer probably touches 70 miles per hour twice. right? So you're going slow, 60, then you go through 70, you've touched 70, and now you're up to 80, spend a little time at 80, you go back through 70, you touch 70 a second time, and then back through 60. So you're driving part of your trip around 60, part of it around, it all averages out to 70, but there's no way to do that without touching 70 miles per hour on your speedometer, and that's all it really says. And in fact, the speed traps that time you, when they just say, we timed you from this mile marker to that mile. We didn't actually see you go 70 miles per hour. Nobody witnessed it, no radar gun. They're using the mean value theorem in reality. And that's because the fact that they're only using your average speed. They never witnessed you going 70 miles per hour. Maybe there's a police officer at mile marker 0. He hits you with a radar gun. You're going 60. You're not going to get a ticket. Now you're at mile marker 100. You're leaving the area. Another police officer hits you with a radar gun. You're going 60. But they still write you the ticket because they timed you and they said your average speed was 70. Guaranteed that your speedometer touched 70, probably even higher than that. And that's the basically the argument they use. And it's mean value theorem. It's exactly what we're doing now. Thanks for your time. Please look at the homework for this section. Make sure you're doing the requirements. Make sure you're talking about the promise, and then also fulfill the promise with calculus by doing f prime equals 0 or f prime equals the slope of the secant line. Thanks a lot.